Reality doesn't work the way you think it does. Right now, at this very moment, particles around you are making choices that nobody can predict, not even in principle. And here's the kicker. The greatest minds in physics have proven that this randomness isn't just because we lack information. It's built into the fabric of existence itself. That's not philosophy. That's measurable, repeatable science. Imagine throwing a ball that should roll in every direction at once, spreading out like ripples on a pond. But when you look down, there's only one track, one path, as if the ball decided mid-flight to commit to a single direction. That's not just weird. That's reality at the quantum level, and it contradicts everything physics says should happen. Today, I'm going to walk you through one of the most mind-bending problems in quantum mechanics, a puzzle that even Einstein couldn't solve, and show you why physicists are still arguing about what it means for the nature of truth itself. But first, hit that subscribe button and turn on notifications, because content like this takes serious research, and subscribing helps the algorithm show you more deep dives into the mysteries of our universe. Let's go back to October 1927, Brussels, Belgium, the 5th Solvay Conference on Physics. Picture this, a room filled with arguably the most brilliant scientific minds ever assembled in one place. We're talking about Erwin Schrödinger, Werner Heisenberg, Wolfgang Pauli, Paul Dirac, Louis de Broglie, Niels Bohr, Max Planck, Marie Curie, and Albert Einstein, all in the same room, all focused on one question: what is reality? This wasn't just an academic debate. This was an intellectual war. On one side, you had the quantum mechanics camp, led by Bohr and Heisenberg, arguing that reality at its core is probabilistic, fuzzy, undefined until you measure it. On the other side, Einstein, who believed that the universe had to be deterministic, that there had to be some deeper layer we just hadn't discovered yet. He famously said that God doesn't play dice with the universe. But there was another problem Einstein raised during that conference, one that doesn't get nearly enough attention, and it's far more troubling than the dice question. Einstein described something simple: a radioactive atom sitting in a device called a cloud chamber. When the atom decays, it shoots out a particle, an alpha particle, which is basically a helium nucleus. Now, according to the math that everyone at that conference had spent years developing, this particle should behave like a wave, not sort of like a wave, exactly like a wave. And waves don't travel in straight lines. They spread out. If you drop a stone in water, you don't get a single ripple shooting off in one direction. You get expanding circles moving outward equally in all directions. That's what the equations predicted for these particles too. But here's the problem. When you actually watch what happens in a cloud chamber, you don't see expanding spheres of mist. You see sharp, straight tracks, clean lines shooting off in one specific direction. Einstein pointed at this and said, "How can we reconcile what the math tells us with what we actually observe? How can something that's supposed to be a spherical wave appear as a definite line in space?" This question sat unanswered for years. It became known as the Mott problem, named after the physicist who would later tackle it. Let me show you what this looks like in practice. Imagine injecting radioactive radon gas into a cloud chamber. If every alpha particle emitted from those radon atoms has a wave function spreading out spherically, the entire chamber should just fog up uniformly. But that's not what happens. Instead, you see streaks, dozens of them, straight lines appearing randomly throughout the chamber, each one representing a single particle that supposedly should have been everywhere at once. Now, before we get to the solution, we need to understand what an alpha particle actually is and how it escapes from an atom in the first place. An alpha particle consists of 2 protons and 2 neutrons stuck together. Before it's released, it's trapped inside a much larger atomic nucleus, held there by the strong nuclear force. Inside that nucleus, it exists as a standing wave, kind of like a vibration trapped inside a box. The walls of that box are created by what physicists call a potential barrier. But quantum mechanics allows for something bizarre called tunneling. Even though the particle doesn't have enough energy to break through that barrier classically, there's a probability that it can appear on the other side. It's like if you threw a ball at a wall, and every once in a while, instead of bouncing back, the ball just appeared on the other side without breaking through. That's quantum tunneling. So if you kept checking where the alpha particle was, most of the time you'd find it inside the nucleus, but occasionally you'd find it outside, having tunneled through. Once it escapes, everything changes. The wave function is no longer confined. It becomes a traveling wave, expanding outward in every direction simultaneously. And because the nucleus itself is almost perfectly spherical, there's no reason for the wave to prefer one direction over another. The math is crystal clear: equal probability in all directions. A perfect expanding sphere of possibility. And that's where reality seems to break the rules. We don't observe spheres. We observe lines. Single, definite, unshaping hand. Straight trajectories. The particle doesn't go everywhere. It goes somewhere specific. So what's going on? Enter Neville Mott. 2 years after Einstein posed the question, Mott published a paper with a deceptively simple title: The Wave Mechanics of Alpha Ray Tracks. In it, he made a crucial observation. Everyone had been thinking about the alpha particle's wave function in isolation, as if it were the only thing that existed. But that's not realistic. The cloud chamber isn't empty space. It's filled with millions of atoms, each with its own wave function. And those wave functions don't just sit there minding their own business. They interact with the alpha particle's wave function quantum mechanically. When the alpha particle's wave interacts with even a single atom in the chamber, something remarkable happens. They become entangled. Their wave functions merge into a single combined state. Mott started with the simplest possible case: just 2 atoms plus the alpha particle. Even with this minimal setup, the mathematics were brutal. Remember, this was decades before computers. Everything had to be calculated by hand. But when Mott worked through the equations, he found something unexpected. The combined wave function wasn't uniform anymore. Some regions had higher probability than others. Not just slightly higher, dramatically higher. The probability distribution developed structure. And when you added more atoms to the calculation, that structure became more pronounced. The wave function developed streaks. Regions of almost zero probability, alternating with regions of concentrated probability. The more atoms you included, the sharper those streaks became. This is the key insight. When you account for the environment, when you include all those other wave functions interacting with the particle, the spherical symmetry breaks down. The combined system naturally produces linear structures. Classical-looking paths emerge from purely quantum equations. This phenomenon is called decoherence, and it's one of the most important concepts in modern physics. Decoherence explains why we always see well-defined tracks. Particles are never truly isolated. They're constantly interacting with their surroundings, and those interactions sculpt the wave function into distinct paths. Once the alpha particle commits to one of these paths, it can no longer interfere with the others. You couldn't take that particle and run it through a double-slit experiment to see interference patterns. It's locked into behaving like a classical trajectory. This seems like it solves the problem, right? We now understand why waves produce straight lines. Case closed. But hold on. There's something deeper here that decoherence doesn't address. Think about what we just said. When you include all the atoms in the environment, you get a wave function with multiple streaks. Not one streak, many streaks. In fact, for a spherical source, the fully decohered wave function predicts an infinite number of possible straight-line paths, all equally likely, pointing in every possible direction. The math doesn't pick one. It gives you all of them simultaneously. But when you actually look at the cloud chamber, you see one specific track, not a superposition of tracks, not multiple tracks at once, one track. So here's the question that decoherence can't answer. Which path does it actually take? Now here's where things get really interesting. Drop a comment below with what you think. Do you believe there's something we're missing? Some hidden variable that determines the path? Or is the universe genuinely rolling dice every time a particle decays? I'm curious what you think, because physicists are still divided on this. The question we're left with is fundamental. Decoherence tells us why we get tracks instead of spheres. It explains the structure. But it says absolutely nothing about which specific track appears. And this isn't a limitation of our measuring equipment or our knowledge. It's not that we're missing some piece of information that would let us predict the outcome. According to quantum mechanics, there is no such information. Any direction is equally probable. The choice is fundamentally irreducibly random. This is what's called the measurement problem, and it's arguably the deepest mystery in all of physics. A lot of people think decoherence solves the measurement problem. It doesn't. Decoherence explains why quantum systems appear classical. It explains why superpositions seem to collapse into definite states when they interact with large environments. But it doesn't explain why you get this result instead of that result. It doesn't tell you why the particle went left instead of right. Let's make this concrete. Imagine you're watching the cloud chamber, and you see an alpha particle streak appear at exactly 37.4 degrees from vertical. Why that angle? Why not 37.5 degrees? Why not 90 degrees? Decoherence says all those angles were possible. The environment created distinct pathways for all of them, but only one manifested in reality. What selected it? Einstein's original question still haunts us. Does God play dice? Is our universe fundamentally random at its core? Or is there something deeper, some hidden layer of reality we haven't discovered yet? Some variable we can't access that actually determines the outcome. This isn't just philosophy. This is a question about the nature of physical law itself. There have been attempts to avoid this conclusion. One of the most famous is the many worlds interpretation of quantum mechanics. You've probably heard of it. In the context of our alpha particle experiment, it makes a radical claim. None of the possible paths is uniquely selected. Instead, every possible path happens. Each one occurs in its own separate branch of reality, its own parallel universe. According to this view, there's no collapse event. The wave function never chooses. It just keeps evolving, splitting into countless versions. Somewhere in the multiverse, there's a version of you watching that alpha particle go left. In another branch, it went right. In another, it went straight up. Every possibility is realized somewhere. The wave function doesn't collapse. Reality does. This sounds elegant at first. It seems to solve the problem by saying there is no problem. Nothing is random because everything happens. But when you dig deeper, this interpretation creates more questions than it answers. Here's the first issue. If every possibility occurs, What does it even mean for something to happen? When we say the particle took a specific path, we mean that path was actualized in our reality, while the others weren't. But in many worlds, all paths are equally real. So what distinguishes your experience of seeing one outcome from the countless other versions of you experiencing different outcomes? The interpretation doesn't give a clear answer. The second issue is more technical, but even more problematic. In the case of our alpha particle, its direction of travel is a continuous variable. That means there aren't just many possible directions. There are infinitely many. Not just countably infinite, like the integers, uncountably infinite, like the real numbers. Even after decoherence, even after the environment has carved out distinct paths, there's still a continuum of possibilities. But that creates a paradox. In the real world, we don't observe infinitely many distinct tracks. If two directions differ by just a trillionth of a degree, they would create identical, completely indistinguishable marks in a detector. Our measuring devices have finite resolution, so when do two nearly identical paths count as the same path versus different paths? When do they split into separate universes? Decoherence doesn't answer this. It tells us when paths stop interfering with each other quantum mechanically. It doesn't tell us when they become ontologically separate realities. The many worlds interpretation doesn't have a clear rule for when two almost identical outcomes count as different branches of the multiverse. This is known as the preferred basis problem. Think about it this way. If paths differing by a trillionth of a degree are separate universes, then there are uncountably infinite universes. But if they're the same universe until they differ by a measurable amount, then who or what decides what counts as measurable? The interpretation doesn't say. It just pushes the mystery behind a curtain of infinity. Here's what I think is really going on. Saying there are infinite universes doesn't solve the original problem. It just hides it. It replaces one mystery, why did I experience this outcome, with a bigger one. Why do infinite versions of me experience infinite outcomes that I can never define or detect? You've traded a concrete question for an abstract one that can never be tested. The many worlds interpretation avoids the collapse problem by denying that collapse happens, but it doesn't explain why your branch of reality contains the specific result it does. And that was Einstein's original question to begin with. Why this and not that? The interpretation answers that by saying both this and that happen, just in different places you can never reach. But that's not really an answer. It's a redefinition of the question, and there's a cost. The many worlds interpretation requires you to believe in an infinite number of universes, none of which can ever be observed or tested, all to avoid admitting that outcomes might be fundamentally random. That's a heavy metaphysical price to pay. You're introducing infinite, unobservable entities to preserve determinism. But if those entities are unobservable in principle, are you really doing science anymore? Or are you doing philosophy disguised as science? I'm not saying many worlds is wrong. I'm saying it doesn't solve the mystery. It reframes it, and in doing so, it introduces problems of its own that are just as deep as the ones it's trying to solve. The preferred basis problem is real. The question of when branches split is real. The question of what it means for something to happen in an infinite multiverse is real. These aren't minor technical details. They're fundamental conceptual issues. So where does that leave us? We've got decoherence explaining why quantum waves look like classical particles. We've got the measurement problem asking why we get specific outcomes instead of superpositions. We've got many worlds trying to avoid randomness by multiplying realities. And we've got Einstein's ghost still asking whether God plays dice. The honest answer is, we don't know. We have the math, we have the predictions, we have experiments that confirm those predictions to absurd levels of precision. But we don't have consensus on what it all means. Is randomness fundamental? Are there hidden variables? Do all possibilities happen somewhere? After a century of quantum mechanics, these questions remain open. What we do know is this: when you watch a cloud chamber, when you see those white streaks appearing one after another in random directions, you're witnessing something profound. You're seeing the boundary between the quantum and the classical. You're watching wave functions decohere in real time. You're observing the moment when possibility becomes actuality. And as far as our best theories can tell, nothing in the universe, not even in principle, can predict where the next track will appear. That's not ignorance, that's nature. The Mott problem shows us that decoherence explains the how, but not the why. It tells us why we see tracks, but it can't tell us why this track instead of that one. And maybe, just maybe, that's because there is no why. Maybe the universe really does make choices that aren't determined by anything. Maybe at the deepest level, reality is genuinely creative, genuinely open, genuinely free. Or maybe Einstein was right. Maybe there's a deeper layer we haven't found yet. Maybe somewhere beneath quantum mechanics, there's a theory that puts the determinism back in. Maybe the dice aren't random. Maybe they're just weighted in ways we can't see. I don't know which answer is right, but I know this: the question matters, because how we answer it shapes what we think is possible, not just in physics, but in existence itself. If the universe is fundamentally random, then novelty is built into reality. If it's deterministic, then everything that will ever happen was encoded at the Big Bang. Those aren't just different physics, they're different philosophies of being. But there's another quantum mystery that might be even stranger than this one, and it has to do with what happens when you try to observe a particle without actually looking at it. That video is coming up next on your screen, and trust me, it's going to break your brain even more than this one did. If you made it this far, drop a comment with the word decoherence so I know you stuck around for the whole deep dive. And if you haven't subscribed yet, now's the time. Hit that button, because we're just getting started with the weird side of reality. Thanks for watching, and I'll see you in the next video.